Great. So tonight I'm going to be talking through human memory and attention, which are sort of two separate topics of your psychology course, but they're quite related, and the sort of structure we'll follow is quite similar. I'm going to mainly cover the left side of your syllabus, so just trying to talk through and cover the key points. If at any point something doesn't really make sense or you want me to clarify something, please just unmute. There's not that many of you in here, and that's great in that sense. So please do feel free, but obviously I'll also leave time for questions at the end of each section. So here's your syllabus. I'm not going to bore you by just going through it, but we're going to start by talking about some of the anatomy of memory, then about the characteristics of memory, and finally sort of memory more in practice, and when memory tends to go wrong. So the neuroanatomical basis of memory, the first point is that there's no one area of your brain that memory is localized in, but classically you hear of the medial temporal lobe, which includes regions like your hippocampus. And the clinical relevance of that is that in Alzheimer's disease, for example, that's the predominant region of degeneration. But there's also lots of other regions. So you also hear about the medial diencephalic region, which includes your mammillary bodies. And clinically, that manifests, for example, in Wernicke-Korsakoff syndrome. So if someone has a thiamine deficiency, their mammillary bodies tend to degenerate, and that leads to quite a profound anterograde amnesia. But as I said before, it's not so simple. So lots of different brain regions are involved in memory. So for example, the elements of memory that rely more on skills, particularly on motor skill, are localized, for example, in the cerebellum. Briefly, how do we know any of this? So it's important to recognize that things have moved on. So early on, our studies of memory were based on people that, for example, had suffered quite horrific injuries and studying what deficits of memory they had. Whereas more recently, and there's an example I'll talk you through, we've moved on leaps and bounds, and we can now probe memory on a molecular basis. And if you were writing essays, it might be interesting to incorporate the sort of different ways in which we've understood memory. So you've probably heard of this patient before, but I'm just going to recap because it's really illustrative in terms of the different anatomical areas involved in memory. So patient HM was a patient quite some time ago in America that had a quite profound epilepsy. And so the neurosurgeons decided to do what we call a bilateral medial temporal lobectomy, which just means taking out the medial temporal lobes on both sides, including the hippocampus. So that unfortunately left patient HM with quite a profound memory deficit. Importantly, though, the memory deficit was mainly in declarative memory, which is the sort, and we'll talk through the different types of memory later, but that's the more factual memory, i.e. knowing that. So for example, given a maze on different days to complete, patient HM had no previous knowledge of having completed the maze and didn't recognize the maze, yet each day would get slightly better at it. So that shows that whilst there was no declarative memory, having had the medial temporal cortex taken out, there was still some degree of the more unconscious types of memory, so procedural memory. But of course, this procedural memory wasn't functioning quite normally, so it was severely reduced in power. So as I said, we're going to talk through the types of memory. So short-term memory has three main functions, really. It's a short-term storage space in which you can use it as a workspace. So for example, doing mental maths. And finally, it's the site where you store memory, which is then being transferred to long-term memory. And people have theorized about its capacity. So for example, one person you might hear about is Miller, who said that the magic number is 7 + 2 based on the number of things that students could remember in a string of letters and numbers. But I wouldn't really spend too much time thinking about that because it really depends on, the size of thing you're remembering. But in summary, it's a small workspace which you can then use to do calculations or to transfer to long-term memory. So in contrast, long-term memory is a long-term storage space, and it's split into explicit memory and implicit memory, which also have their own subcategories. So explicit memory is declarative knowledge, and that's knowing that, i.e. knowing facts and things like that, or knowing experiences. So your episodic explicit memory is personal experiences, so it might be events you've witnessed or something like that, whereas semantic memory is facts, ideas, and concepts, and more how things relate to each other. So a clinical relevance of that is that you can get a quite specific subtype of dementia called semantic dementia, which specifically affects the semantic memory. So someone might be quite fluent in their speech, and they might remember their personal experiences quite well. But when asked to describe, for example, the meaning of something or how something relates to something else, they will have quite significant difficulty with that. In contrast, the other broad category is implicit memory, and that's more procedural knowledge and knowing how things work, knowing skills, some of which might be motor skills. And as we said before, for example, in patient HM, the cerebellum plays a key role in this. And patient HM was able to play table tennis. Each day he didn't forget how to play table tennis because that's localized in regions of the brain other than the medial temporal cortex. So we have the short-term memory and we have the long-term memory, and obviously information has to move from the short-term to the long-term. And that happens through a combination of processes which occur at different levels. So on a molecular basis, at a synapse, you have long-term potentiation. That allows cellular changes. And then probably most important to your understanding is systems changes. So short-term memory is classically thought to be more localized in the hippocampus, and long-term memory is classically localized more in the cortex. So people have tried to understand memory consolidation through models. So the standard model suggests that, quite simply, there's just a transfer of information from the hippocampus, i.e. the short-term information, to long-term information in the cortex. And that eventually all of the information in the cortex, the long-term memory, becomes independent of the hippocampus. So that sort of suggests that the cortex eventually functions independently of the hippocampus. Whereas another alternative model is the multiple trace theory, which incorporates the standard model but builds on it, suggesting that not only is information transferred from the hippocampus to the cortex, but that different types of information might be stored differently in the long term. So, for example, it distinguishes between the semantic and the episodic memory. So, for example, the hippocampus would be involved in the episodic memory, whereas the semantic memory becomes somewhat independent of the hippocampus, which would fit more with the standard model. And a really, really important concept to understand, particularly in your psychology syllabus, is that memory is reconstructive. So what do we mean by that? Well, to have a memory, information has to be firstly perceived. So say I was remembering something I saw, I have to perceive it accurately, i.e. my eyes and my brain have to be working well enough to actually see that event. Then I have to encode that event, so convert whatever I see into some sort of signal in my brain. That signal then has to be stored in my brain, potentially for quite a long time, whilst my brain's doing a lot of other stuff, and then that information has to be retrieved. So there are four key processes which can go wrong or can at least be influenced by essentially anything else that's going on in the brain. So to give some examples as to things that interfere with the process is involved in memory. We have our previous experiences, so how we see the world based on what we've already seen. We have the accuracy of perception, which I touched upon. So, if I don't quite see something correctly, but I encode what I thought I saw, then even if the rest of my memory works perfectly, that memory could potentially be quite inaccurate. And finally, our later experiences. So as I said, memory is stored for quite a long time, and then it has to be retrieved. And say I accurately perceived something, I accurately encoded it, but then it was being stored in my brain whilst my brain learned lots of new information. It might be that memory changes. So it's really important to recognize that memory is quite a dynamic thing, and something so distributed in our brain is obviously subject to influence from all the rest of the areas of our brain. So one example of these things that can interfere with memory is what we call schemas. And they're basically just our mental representations of essentially anything. And obviously they affect the way we reconstruct memory. So for example, a stereotype, which we hear often, is a schema about people. And so, if we have a particular stereotype of someone, when we're reconstructing our memory about them, that memory might not be quite accurate. So there's lots of proof that memory is reconstructive. We can start just by thinking about all those times that we've remembered something differently to someone else that saw something. But there's also formal, sort of more psychometric evidence. So as an example, Hannigan and Reinitz in 2001 used these depictions of piles of oranges, and they either showed someone a depiction of loads of oranges falling over, or of someone taking an orange from the bottom of a pile, causing theoretically a risk of oranges falling over. But importantly, in either of those cases, they'd only be shown one of those two things. So they'd be shown someone taking an orange, but they wouldn't be shown them toppling over. Or they'd be shown them toppling over, but they wouldn't be shown the original event, which was someone taking one from a pile. Yet when asked to recall, there was a really high rate of error. So people were quite confident that they'd seen both, i.e. they'd seen someone take an orange and then they'd seen it topple. There's another example which is quite famous, which I haven't included in here, which is the example of people being asked to recall having been shown videos of car crashes, and their reconstructive memory could be really easily influenced by the way in which the questions they were asked about the recall. So if they were asked what happened when the cars smashed together, they were more likely to report that there'd been broken glass on the road, for example. And something I won't dwell on for too long, because I know this is a revision lecture and I really do want to keep to your syllabus. But if you do decide to write an essay on memory, lots of people will write loads about the more classical cases, patient HM and people like that. But it's important to recognize that there's been some really cutting edge advancements in our study of memory. And now we're at a point where we can really study memory on a molecular basis. And this is one of the coolest experiments I came across in my FHS, because I picked neuro, and it still sticks with me. So basically, this group were trying to essentially find the cellular basis of memory. And to do that, they wanted to tag cells that represent a memory and then reactivate those cells and see if it triggered the memory again. So they put rodents in quite a fearful scenario, and they used some really clever technology called optogenetics, which might have crept into your syllabus by now, but I don't think it was in our second year. And in doing that, they can basically tag neurons that are active. So in the fearful scenario, they could tag the neurons that they decided represented fear, or at least this fearful memory. Then they could reactivate these neurons later. And when they did reactivate these fear neurons using light, which is the principle of optogenetics, it led to the very same fear response as when they were actually in the fearful scenario. But quite an obvious critique, if this was all they'd done, would be that, oh, maybe they've just, caused a lot of strange brain activity by reactivating all sorts of neurons. And even if they reactivated any neurons, they'd cause this freezing response. But importantly, they did have controls. So rather than doing a fearful scenario, they also did the same experiment in a neutral scenario. And when they did that, there was no reactivation of the same response. So it wasn't just that they're reactivating cells. It seems that it is specific to those fear cells. So what can you take from this? Basically, we moved on a lot from studying massive lesions of memory, and that eventually we might be able to study on a molecular basis how memory works. And we already are doing so. So as I touched on before, and this is something that tends to come up in your questions, not only is memory reconstructive and therefore likely to cause false memories, but this has real world implications. So in the legal sphere, obviously, if someone recalls something inaccurately, this can lead to someone, going down for a crime they didn't commit, for example. But also in the medical sphere, this is really, really common. So one of the sort of threads of examples commonly used is primary care, or any medical consultation, in fact. So Kessels et al. In 2003 reported that around half of the information recalled from a consultation with a medical professional is incorrect. So having an idea of the fact that memory is reconstructive and memory can be false is really important for when we're practicing as clinicians. Another example is quite an extreme example of false memories. So as I touched on before, Korsakoff syndrome is the late stage of Wernicke-Korsakoff syndrome, and it's where your mammillary bodies degenerate. And you get this really frank clinical picture of confabulation, where someone will be completely convinced of things that didn't happen, and they'll genuinely believe them to be true despite plenty of evidence to the contrary. Another thing mentioned on your syllabus is the primacy and recency effects. So this is particularly important in your short-term memory. So your primacy effect is basically that we're more likely to remember items that were at the beginning of a list. And this is partially explained by the fact that your brain probably has a bit of time to go over these items and to rehearse them. Whereas in contrast, the recency effect is that we're more likely to remember items at the end of a list. And that's partially explained quite differently from the items being fresh in your working memory. I wonder if someone would be kind enough just to unmute and just to check whether I've lost you guys, or whether the pace is okay.
Yeah. It's okay.
All right, good stuff. Just want to check. And does anyone have any questions at this point? Okay, I'll move on then. So this primacy and this recency effect form this curve called the serial position curve, which is definitely on your syllabus. So essentially, the probability of recalling something, as you said before, because of the primacy and recency effect, is highest at the highest of something that was presented first to you and something that was presented last to you. So for those things that are early on, over on the left of the curve, the probability of recall correlates basically exactly with the total rehearsals, whereas from sort of position 13 onwards, i.e. the later things in a series of pieces of information presented to you, these two lines break apart. So the probability of recall starts to increase again, despite the fact that you're not able to rehearse that item. And so it just shows that, as per the primacy and recency effects, the primacy effect is based on recall, is based on rehearsals, and the recency effect is based more on something being fresh in the memory. So it's independent of rehearsal. So amnesia, as you know, is inability to remember something, but there are lots of different types of amnesia. So anterograde amnesia is difficulty forming new memories. And for example, amongst students, many of you will have experienced anterograde amnesia from a night out. So if you're quite intoxicated, from that point onwards, you aren't able to form new memories. Whereas retrograde amnesia is difficulty remembering things that have already happened, i.e. difficulty accessing old memories. And again, mentioned on your syllabus, there is Ribot's law, which basically just says that there's a time gradient in this retrograde amnesia. So recent memories are more likely to be lost than more remote memories. So there's lots of reasons this might happen. So one might be that because of different anatomical locations. So as we remember, the long-term memory is more likely to be in your cortex rather than your hippocampus. And it might be that the types of amnesia that result in retrograde amnesia selectively affect those regions, but there's lots of other explanations as well. So I wouldn't get too bogged down in that. And going back to our friend patient HM, we can look at his amnesia and we can look at the different types of his amnesia. And it's quite illustrative, again, of both Ribot's law, but also the anatomical differences in memory localization. So his retrograde amnesia had a clear temporal gradient. So that reflects Ribot's law. And his anterograde amnesia, as we spoke about, was much more of a declarative problem than a procedural problem. So he didn't remember facts, he didn't remember who he was, but he did remember skills, and he didn't forget how to play table tennis. So it demonstrates that there are anatomical differences in memory localization. So just to cap off memory, these are some of the types of questions that might be asked of you guys in your exams if you chose to do an essay on memory. And you'll note that they focus particularly on the reconstructive nature of memory, the fact that this leads to false memories, and that these have a lot of implications. So I'd probably focus on these sort of large questions in memory. And yeah, we've got plenty of time for questions throughout. So if anyone wants to ask anything now about memory, do feel free. Or if you want to save it until the end of attention as well, that's fine. So I'll just give it a little while. Great. So we're going to talk through human attention now. So as before, I've got your syllabus up here, and we're going to focus on those points on the left. So particularly the functional anatomy, how attention functions, the different types of attention. So mentioned in your syllabus is the sustained and spatial attention, the differences between attentional loss and sensory loss, attention planning and intelligence, and then when attention tends to go wrong. So there's some clinical syndromes that we see quite a lot of in clinical school, particularly in neuro and psych. And they're really interesting, and they link really well to the functional anatomy of attention. I'll briefly cover some of these points on the right of your syllabus, but I'm trying to just keep this fairly succinct and cover the main points of your core syllabus. So what actually is attention? And it's a really difficult thing to describe at times. But one way might be that it's the cognitive process of selectively focusing on one thing whilst ignoring other things. And it's really, really important because it basically allows us to do anything. In that without proper attention, we wouldn't really be able to focus on our activities of daily living. We wouldn't be able to sit and watch a lecture at all. So it allows us to selectively apply salience to a restricted set of stimuli, which could be internal or external, and to therefore facilitate processing whilst inhibiting other distracting information. So the anatomy of attention. So like with memory, it's important to note that attention is fairly global. There's no one area where you say that this is attention, but you guys know that, and you know better than to just define areas based on one function. So it's distributed in diverse brain regions. But further than that, whilst lots of brain functions require network function, attention seems to be one of those that really function as a network. And so whilst there's lots of different regions, they also have to work together as part of one well-oiled machine. And I'm just going to touch on a few of the areas. So the one you classically hear about is your parietal cortex, but you've also got a few more. So the frontal eye fields and the cingulate gyrus. So I've got a few slides coming up where we just talk through them and talk through some examples of evidence as to how we know that they're involved in attention. Importantly, how do we know any of this? So again, like with memory, our really earliest understanding was from people that had brain lesions. And it might be that someone's, very unluckily had some sort of trauma to, specifically to their regions that control attention. But actually, a lot of this has been understood from strokes. And we'll talk about those types of strokes that do affect attention and cause a syndrome called neglect. But moving past that, most of the modern understanding coming out now, particularly in cognitive neuroscience and in psychology, is based on functional MRI. And that's probably something you've come across quite a lot, which functions basically by measuring brain activity based on glucose levels. But there are obvious issues with the studies based on fMRI, because there's a bit of an overinterpretation problem. So just because a brain region is active doesn't mean it's sort of essential to that function. And there's a bit of a disconnect there. And it's sometimes termed neophrenology. It's something we won't dive into too much here. So the first and probably the most important brain region to understand in terms of attention is the parietal cortex. And classically, it's your right-sided parietal cortex that's most essential to attention. So damage to your right-sided parietal cortex leads to neglect of a person's left side often. And as you know, the cortex typically represents the opposite side. So the right side of your cortex represents your left. So damage to your right causes a deficit on your left. And so we'd expect, as with things like a stroke that causes sensory loss or causes motor weakness, we'd expect the same essentially on the opposite side, because the cerebral cortex is symmetrical. But interestingly, it really seems to be the right-sided parietal cortex that's vulnerable to damage and causing left-sided neglect, because similar lesions on the left side of the cortex result in quite a lot milder deficits on the right. And there are lots of explanations for this. It definitely suggests that there's some degree of localization of attention function to the right side, because that's where the lesions really lead to neglect. And neglect is something we'll delve into more later. But it might be that there's also some degree of anatomical redundancy explaining this. As I said before, there's lots of brain regions involved in attention. So your frontal eye fields are also really important. And Gittelman et al., for example, in 2002, used fMRI to measure brain activity during a visual search. I've highlighted search because it's important to clarify what exactly visual search is. So it's not just looking at something, but it's sort of goal-directed activity for which attention would be really important. So to demonstrate that something's involved in a search, you have to show that someone's actually looking at that thing. So you'd have to also measure the activity when they were just looking at it passively and not actually in a way that's important to a task or anything like that, and to compare the brain activity in a search versus when you're just passively looking at something. So it wasn't just the frontal eye fields that were very active, but also your superior colliculus. And as you may know from your neuroanatomy, that's a really important region in your eye movements. But it seemed that the superior colliculus activity was influenced by the activity in some cortical regions, particularly the frontal eye fields. I've said here again that we have to be slightly careful with interpreting fMRI, and we often make assumptions, but we cannot be sure of causal roles. In terms of the frontal eye fields, the clinical relevance of them is that in a stroke, if your frontal eye fields are affected, your eyes will point towards your frontal eye field that is affected. And finally, I mentioned the cingulate gyrus. So this is also an area that's classically mentioned in attention, and it seems to be involved in areas where there's sort of conflict between potential behaviors. So this experiment that we're going to talk about relies on the Stroop task. So if you have a look at it, essentially there are a number of words which spell out a color but are also in a color, and that color might be the same as the word it spells out, but it's often different. And so it can be quite confusing because one part of your brain wants to name the color based on the word it's reading, whereas other parts of your brain want to name the color based on the actual color itself. And so Erickson et al. In 2004 used fMRI, and they were looking particularly at the anterior cingulate cortex. And they showed that the degree of activity in this region was really affected by any sort of task that had behavioral conflict. So the Stroop task would be a good example of that. But importantly, it wasn't just a static thing. So as the participants got more used to the Stroop test, the activity in their anterior cingulate cortex decreased. So maybe it's probably a reach, but you could say that the anterior cingulate cortex might function in early conflict resolution, which is just one example of a process that requires a lot of attention. So as mentioned in your syllabus, there is lots of different types of attention. And one example is spatial attention. So it does what it says on the tin. It's just selecting a stimulus based on its location in space. So we predetermine the salience or the importance of an object based on the region it appears in. So you could think of this as like a spotlight, and it's been compared to this loads. Like a spotlight, it can move, it can be bigger or smaller. So you could be paying spatial attention to one half of your visual field, or you could just be paying spatial attention to a tiny part of your visual field. And it's really important to understand that your spatial attention doesn't have to be the same as where you're actually focusing your eye on. So you could be focusing straight ahead of you, but covertly paying attention to the corner of your eye. and that's been shown quite a lot. But one example is Posner et al. And that's one example where attention and your sort of sensation don't have to be the same thing. They're quite different, and we'll explain more how they differ and why that's important shortly. So another example of your types of attention is sustained attention. So this is quite different to spatial attention. Conceptually, they're doing the same thing in that you're selectively applying salience to one thing, and that's as we defined attention. But this is the ability to basically focus on something for a long period of time. So, for example, doing quite a boring task for a long time, but that requires you to focus. And this can be measured in continuous performance type tasks, which require constant attention. So, for example, vigilance tasks where a specific sound is presented infrequently and at times that are not predictable, so aperiodically over a long period of time, on a background of other stimuli, which we'd call noise. And the participant has to respond in a way accurately to each of the specific sounds. And you can measure their accuracy, reaction time, latency. So you can get lots of ideas about how their attention's functioning. And the clinical relevance of this might be that if you were doing a workup of someone that you think might be demonstrating features of attention deficit hyperactivity disorder or ADHD, one of the things that would help you in your diagnostic workup is similar tasks like this. So often there's sort of computer-based tasks where someone's given a task that's essentially quite boring, and you're just trying to work out whether they can focus on it for a long period of time or not. So, as I said before, attention and sensation are really quite different. And you can have functioning attention without sensation. You can have functioning sensation without attention. And extinction is where these things sort of collide. So let's discuss this. I hope I'll explain it well. So just to reiterate the fact that attention is not the same as sensation. Someone might not pay attention to one side of their body, but they can still detect things on that body. So it's not that they've lost all sensation on that side of their body. It's just that their brain is paying much more attention relatively to the rest of their body. So attention should definitely be thought of as something that's relative rather than absolute. And to demonstrate this, for example, if someone does have total neglect of one side of their body, they can still detect things if you strongly cue them. So, for example, if they had left-sided neglect and you were asking them to detect sensation on that side, if you made a noise over on that side, they might be much more likely to detect that sensation. Likewise, some people that have left-sided neglect will have no real trouble detecting something on the left if that's the only stimulus they're receiving. So if I had left-sided neglect and you touched my left side, my left arm, I might say, yes, I can feel that. And if you kept that stimulus there and touched the opposite side, so my right arm, because I have left-sided neglect, I'm paying relatively much less attention to my left, despite the fact that ultimately I can feel it. So when you add that extra stimulus to my right, I can no longer really detect that stimulus on my left, despite the fact that I could before, and that's called extinction. So it's basically where the additional of a contralateral stimulus leads them to no longer perceive the original stimulus. And that's one of the classical syndromes we get where attention has been affected. So your syllabus notes attention, planning, and intelligence So there's been lots of attempts to conceptualize the notion of intelligence, and they should all ultimately include attention, because I mean, based on our definition of attention, it would be pretty hard to have any sort of real higher function without some degree of attention, because the brain wouldn't know which stimuli or which thoughts to pay attention to. So one example is the past theory, which is expanded upon briefly in the notes that I've made to accompany this lecture. But I wouldn't devote too much attention to models like this unless you're planning on writing an essay on attention. So I explained extinction before, but it's important to note that that was just one example of it. So it's any neurological disorder which impairs the ability to perceive multiple sensory stimuli of the same type simultaneously. But it doesn't have to be tactile like in the example I gave. So it could be visual, it could be tactile, could be auditory, could be chemical. So it could be any sort of taste, can also be multisensory. And again, it suggests that attention is more of a relative thing. So someone with neglect hasn't got the total inability to pay attention to that side, but just that they relatively pay much more attention to the other side. And again, it's not explained by any sort of simple sensory or motor failure, as strongly cueing can overcome neglect to that extent. So, for example, if someone had motor neglect, touching that part of their body and giving them a sensory cue can help them to use it. Or if someone has sensory neglect, loudly banging on one side of a table could result in more processing of the information on that side. So neglect can be either sensory, it can be motor, it can be sensory motor, or it can be conceptual. So how common is it? This was from a review article, and I've just copy and pasted. So this is Barrett et al. 2006. And as we said before, it's much more common in strokes in the right hemisphere, with estimates of the incidence ranging from 13% to 81%, which obviously a massive gap, presumably reflecting lots of different inclusion criteria, lots of different lesions, lots of different ways of assessing and defining neglect. Importantly, it really depends on the age at which someone has their stroke. So, for example, in people 18 to 50, only 5% had neglect versus 18% in the comparable patients over 80. Maybe a caveat to this is that people between 18 and 50 likely have quite different strokes to those over 80. But even so, there is probably some explanation in terms of the younger brain having more redundancy and things like that, and being able to overcome the attentional deficit through other means. Maybe also being more plastic, so being able to adapt to the lesion and sort of restore function. So yeah, I've touched on this before, but just going to give some examples now. So this is more, we can't know what it's like to have sensory neglect, and I don't claim to, but this is a sort of schematic of how we could conceptualize it might be for someone. So this might be how it appears to them. So if they have sensory neglect of their left side, they really they cannot see that side at normal function. They can see it if they are directed to it, for example. So it again goes back to the difference between the sensation of something and ultimately the representation of it in our brain. And it shows that our sensory function and our attentional function need to interact to accurately see the world and engage with it. So again, this is how someone with sensory neglect might perform in some tasks. So on the left, the person's being asked to copy a clock, a house, and a flower. And their drawings on the right quite clearly show that they neglect their left side. So to them, this drawing will feel completely finished, both because when they first look on the left, they will see mainly the right-hand side of the image, but also when they then copy it, they won't notice that there's, half of a house hanging off, or that half of the clock's not finished, because they're only really paying attention to the right-hand side. Likewise, on the right, someone's being asked to spontaneously draw. And it's interesting to see that it's not the whole of the image. So, the contour of the head and things, but just specific things are missed out. So yeah, moving on, there's a syndrome called dysexecutive syndrome and goal neglect, which is mentioned in your syllabus again. So dysexecutive syndrome is basically just a pattern of executive dysfunction, which normally results from brain damage and incorporates dysfunction in the cognitive, behavioral, and emotional domains simultaneously. And most commonly, it's associated with frontal lobe damage. In contrast, goal neglect is when participants are aware of a rule and can repeat the rule back to you and seemingly understand the rule, but don't follow it. So I mentioned before this idea of conceptual neglect, and it's something that's quite difficult to get your head around, but it's really important to demonstrate that your attention isn't only to external representations of things, it's also to your internal representation. So, for example, your dreams, or if we try and imagine something now, we might see a mental image of it, whereas someone with quite a severe deficit in their attention might only imagine part of that mental image. So this was a really interesting experiment by an Italian group, Quariglia et al., where basically they asked a load of patients who were all familiar with the same area of Milan to imagine that they were standing in front of the cathedral in Milan, and basically to describe what they would be able to see if they were looking in one direction. And when they did that, these people who had left-sided neglect only really described buildings that would be on the right side of their mental image. And so maybe you could say, well, maybe these people only shop on that side of the road. They only know that area of the road. But then the group said, well, how about you turn around in your mental space and you look the other way? And this time, the participants selectively described the opposite side of the road. So it's not that they're more familiar with one side of the road. They know both sides of the road, but when they're trying to remember it in their head, they can only remember the side on which their attention is still functioning completely normally. So, as mentioned in your syllabus, attention, it's common in strokes, and therefore it's a key target of rehabilitation. And it is supported by evidence, so particularly visuospatial rehabilitation after a right hemisphere stroke, which would be the classical stroke causing left-sided neglect. There's several options available. So, for example, visual attention therapy, which basically involves teaching people to use techniques like visual scanning to retrain them to actually actively look towards the side on which they have neglect, i.e. the side contralateral to their lesion. There have been attempts to more globally enhance attention in people that have had brain lesions, for example, with dopamine. These have been much less successful and aren't used. So it's really a case of therapy over the sort of biological approach here. And we mentioned ADHD before. So that's something where it's defined by an attention deficit as one of the sort of three key features alongside hyperactivity and impulsivity. And that might be a case where you think we need to rehabilitate attention. And again, in this case, it's not just about, there's no switch we can flick on attention. It needs to be according to sort of a biopsychosocial model. So biologically, you can enhance attention with stimulants like methylphenidate, but most importantly, probably, these people need psychological therapy potentially, and they will also benefit from help in the more social domain. So social skills training, parental support, educational support, and things like that. Finally, there's just something on your syllabus called change blindness, which I know in the lecture it was quite a prominent feature, and I've seen it feature in some of your questions. And this again goes back to the difference between attention and sensation. So this is basically the phenomenon where a change isn't noticed after a brief visual disruption. So say you're looking at an image, then the image flashes away and comes back, but some small element of that image has changed. Say you're looking at a pond, maybe a duck has moved position or something like that. And when you're looking at the new image, you might be accurately perceiving the new image. If someone asks you to point out where the duck is, I'm sure you could say, well, the duck's there, but you might not have noticed that that's different to the previous image. And so this demonstrates that perception and sensation versus attention are different. And I know I keep harking on about that. It would also demonstrate that obviously short-term memory is probably involved quite significantly in attention, because in order to not demonstrate change blindness, A, you have to have attention to notice a change, but B, you have to have short-term memory in order to compare those images in your head. Really interestingly, and I think this is, we're really coming to the end here. One study, Kavanagh et al. In 2004, showed that you can actually modulate change blindness. So they electrically stimulated the superior colliculus of monkeys. As we discussed before, this is an area involved really in sort of visual movements and visual attention, and that led to a significant decrease in change blindness. Whether we could do similar things in humans, I think we're a long way off. So much like with memory, there's a few examples here of the types of questions you might be asked. So the first is, what do studies of change blindness tell us about the relationship between attention and perception? So I've tried to sort of give some examples of this, but obviously far from giving an essay on that. But there's a lot of stuff that you can explore on that. Second is, what is the nature of ADHD? Discuss the symptoms and the correlates at the cognitive and neural levels. And 3, what's meant by the term inattention, and how does inattention affect information processing?